Welcome to the video for Chapter 16. Today we're going to talk about Faraday's law, which is perhaps the most important law in all of electromagnetic field theory. As we're going to see, there's actually a fairly simple form of Faraday's law, which we're going to spend most of our time talking about today, and then there is the more formal representation of Faraday's law, which is the official addition to Maxwell's equations. But I really want to focus on this less formal version of it because I really think that it helps to illustrate the principle of what we're talking about. I remember when I was a student, Faraday's law was completely baffling to me, and that's very frustrating when I look back on it because it shouldn't have been. Faraday's law is actually very straightforward, and the calculations you're going to find are significantly simpler than the ones that we've done in previous calculations. So Faraday's law of induction, I feared it for many years, but I shouldn't have because if we talk about it appropriately, I think you're going to find that it's not so bad. So we're going to determine the voltage appearing around a loop that is subject to a time-varying magnetic flux. We're going to use Faraday's law of induction to determine the current induced in a coil subject to a time-varying magnetic flux. And we're going to calculate the voltage induced across a rotating loop of wire. So it's pretty obvious who I would choose for today's historical perspective. Michael Faraday, he was a British scientist who made just tremendous contributions to many areas of electromagnetic field theory. And you could kind of think of it as if this were volleyball, he set the ball and then Maxwell spiked it, because Michael Faraday's work really did directly lead to the work that Maxwell did, although there were 30 years in between their work. So it's important to know that it wasn't an immediate set and then spike. So let's talk about Faraday's law, and then sort of related to that is Lenz's law. Now we've seen that voltages create currents, and we've seen that currents induce magnetic fields. Today, though, we're going to see that changing magnetic fields will also create or induce voltages as well. Faraday's law shows us that the voltage induced around a closed conductor is equal to the time derivative of the magnetic flux through that conductor. So you can see here in equation 16.1, the voltage around a loop is equal to, and ignore the negative sign for right now, is equal to the time derivative of the magnetic flux, psi sub m. You'll remember that we've previously seen that psi sub m is equal to B times A. It's not. We'll see that there's a more formal version of that equation today. But in general, we've been finding magnetic flux densities for some time. If we multiply that by the area, we get the psi sub m, and if we take the derivative of that, we'll now be able to find a voltage. Figure 16.1 shows exactly what sort of experiment are we talking about. In what circumstances would this be? It's essentially if there's a closed loop, and you can kind of, although I've shown a voltmeter here, you can assume that there is a closed loop that's going there. And if the flux is changing through that loop, so if psi sub m is increasing or decreasing, really for any reason, then we're going to find that there will be a voltage induced around the loop. That is not intuitive. It is not obvious that that would have been the case. We're going to find out how incredibly important it is that that is the case. If this equation didn't hold true, there would be no field of electrical and computer engineering, because we would have never figured out how to create electricity without having these sort of relationship being true. Now the voltage that's induced can be measured directly by a voltmeter, but we're more typically going to find that we'll put a resistor in place so that we can control the amount of current. You know, as I've shown this wire here, there's no resistance in the loop, and so therefore you could imagine there'd be a very large amount, if not an infinite amount of current flowing. We want to put a resistance in there or some sort of element to absorb the voltage to ensure that there isn't an infinite amount of current. Now, there are four basic ways to change the magnetic flux through a loop of wire. You can change the magnitude of the magnetic field. That's about as simple as it gets. You know, the arrows are still pointing in the same direction, but psi sub m would increase or it would decrease, or maybe it's even a time-dependent function. And those are very reasonable ways to change the flux. You can change the direction of the magnetic field. So rather than being perpendicular, as it's shown in figure 16.1, maybe the magnetic field is all of a sudden going to be pointing off in a different direction. So that would be, for example, if you had a fixed loop and you're moving a magnet around it. Well, you would induce a magnetic flux that's going to be changing if you did that. You can change the shape or the size of the loop. So we can imagine a world in which we would adjust the loop. The magnetic flux would remain the same, but the loop would then capture more of that flux. Or you could change the orientation of the loop. So now the magnetic flux is staying the same, but now we're going to be rotating the loop one direction or the other, and that would then cause more or less of the magnetic flux to pass through that loop. We're actually going to see all 4 of these examples in the next few minutes, and so I just want you to be prepared for the fact that I think I've brainstormed all the ways that we can change the magnetic flux, and we're going to see that each of these is valuable to us as electrical and computer engineers. Now, one question is, which direction does the voltage and therefore the current appear? If I come up here, I haven't really shown the polarity of this voltmeter, but maybe the polarity is plus to minus. And if that's the case, then does the voltmeter read positive or does it read negative? We have to specify the sign as well as the magnitude. And the answer to this comes from Lenz's law. Sometimes it's actually even known as Faraday/Lenz's law. But Lenz's law states that the induced voltage will create a current that opposes the direction of the change in the magnetic flux. So it's always good in physical systems when things are very stable. And you could imagine, gosh, if there was a flux that was increasing, if it was increasing and all of a sudden then Lenz's law says we're going to increase it even further, that would lead to instability. But if it's increasing and we're going to cause it to decrease by Lenz's law, then that's more stable. You could imagine, I'm getting behind on my budget, I better decrease my spending, or my expenses have grown too high, I need to decrease my expenses, rather than my expenses have grown too high, I better increase my expenses. That's not the way that it works. So Lenz's law says we will always oppose the direction of change in the magnetic flux. And that's really what the negative sign in Faraday's law represents. So if I come back up to here, this negative sign really comes from Lenz. And if you do everything correctly with 3-dimensional vectors and use exactly the correct unit vectors and use a consistent coordinate system, then that negative sign will in fact take care of Lenz's law. But my advice to you would be, don't put the negative sign in there. Don't really use the negative sign for that purpose, because many times these problems are going to be relatively straightforward, and then we can just apply Lenz's law directly with the right-hand rule to figure out which direction the current and the voltage should be. So I will now begin by omitting that negative sign, but I will then say every time that we solve this problem, we also have to apply Lenz's law. But just know that the official version of Faraday's law includes a negative sign, and that indicates that the induced voltage and current should oppose the change in the direction and in the magnitude of the magnetic flux. So I'm going to omit the negative sign, but I'm also going to include an N in Faraday's law when we get to the next example. But for right now, let's consider this first example. We're going to consider this setup in which the magnetic field increases in strength from 3 Tesla to 6 Tesla over the course of 2 seconds. And I forgot to mention it in here, but I'm going to say that each one of these sides is 50 centimeters. And that probably is already written on your notes because I just forgot to put it in mine. And so if each of the sides is 50 centimeters, it's increasing from 3 Tesla to 6 Tesla over the course of 2 seconds, then the question is how much voltage is induced. Well, we can calculate psi 1. So psi 1 is over here, and that's equal to 3 Tesla times 0.5 meters, the quantity squared, which is going to give me 0.75 Webers. And then so that's psi 1. Psi 2 is going to be equal to 6 Tesla times 0.5 meters, the quantity squared, which gives me 1.5 Webers. Delta psi is going to be equal to 1.5 Webers minus 0.75 Webers, which is equal to 0.75 Webers. I'm going to say that V of t then is going to be equal to d psi dt, and because here we don't have instantaneous changes, it's an average change, this is going to become delta psi over delta t. That should be delta t. Then this is going to be 0.75 Webers over the course of 2 seconds. So here we see that delta t is 2 seconds. So this gives me 0.375, and I could write it as Webers per second, but the correct units that I would use are volts. So 0.375 volts. Which direction is the voltage going? Well, notice that when we go from the first situation to the second situation, the magnetic flux is increasing. It's increasingly pointing vertical. That means that I'm going to need the magnetic flux that would correspond to the induced current would need to oppose that change. So it would need to be going downward. And so in order for the voltage to be going downward, in order for the voltage to induce a magnetic field that would go downward, I would need to use my right hand grip rule. And what I'm going to do is I'm going to erase this 50 centimeters just so that I can try to draw a picture here. I'm going to tend to put my thumb, and I apologize for the horrible picture here of my hand, but I'm going to put my thumb in the direction of the current, and then my four fingers are going to curl in the direction that would be downward. So what I'm doing is I'm creating a magnetic flux that is going around this wire like this, and then inside of the loop it's going to be going downward. So that means that the current is going to be flowing in this direction, and then it's going to be flowing in this direction, it's going to be flowing in this direction, and it's going to be flowing in this direction, and the voltage across here would be plus to minus. So it would be clockwise, so the induced current is clockwise when viewed from above. Whenever we say something like clockwise or counterclockwise, we always have to specify that it's going to be when viewed from above. So in previous chapters, we've always said that psi is just equal to b times a, but things are about to get more complicated, and so we need to be more mathematically precise. And it's not just correct to say that it's just b times a. It is the surface integral of b dot ds. And so, of course, if b is constant over the surface, then it would just become b times a, as long as b and ds are in the same direction. Remember that ds is perpendicular to the surface, and if b is also perpendicular to the surface, and if b is not changing over the entire surface, then it just reduces down to b times a. But I could imagine now, if b is not perpendicular, then we would need to incorporate this dot product right here. Remember that the dot product is going to include a cosine of theta. So this would be whatever the theta is, where b is different from vertical. So we're going to need to account for that as well. And then, as I mentioned a little bit prematurely earlier, if there is a coil of wire, so we've been talking about what happens if there is a loop of wire, but what happens if it's a coil? You know, what if there are multiple loops that are on top of each other here, and if there are n turns? Well, then you can imagine that there would be n times as much voltage. Each one of these loops, if you will, is in series with one another, so those that voltage will be induced on each of the loops, and therefore they'll all add together, and then you'll get n times as much voltage. So this is actually my preferred version of Faraday's law. I drop the negative sign and I put in an n. If there aren't multiple loops, then we would just say n equals 1. And of course you have to use Lenz's law to determine the direction of the current flow. Okay, well here we have an example where the magnetic flux is not perpendicular to the surface. It starts perpendicular, but then it's not going to be perpendicular at the end. And there are 10 loops in the coil, and over the course of 3 seconds we're going to introduce a 30-degree change in the direction of the magnetic flux. So it's a relatively small change, and it's occurring relatively slowly at about 10 degrees per second. So I'm not really expecting a very large amount of voltage to be induced here, but let's see how much voltage that would be. Once again, I should mention this is 0.5 meters in each direction. And so we see that over here, psi 1 is going to be equal to 3 times 0.5 squared, which gives me 0.75 Webers. And then over here, psi 2 is going to be 3 times 0.5 squared times the cosine of the angle between the magnetic flux density and the normal vector. Well, the normal vector is going to be pointing straight up, and the figure illustrates that it's a 30-degree difference, so that's going to be times the cosine of 30 degrees, and that works out to be 0.65 Webers. Delta psi then is equal to 0.75 minus 0.65, which is 0.10, and V is equal to delta it's d psi dt, but we're going to list it. Oh, I forgot the n. V is equal to n delta psi delta t, which is going to be 10 times 0.1 divided by 3, which is going to give me 0.333 volts, which I'll represent as 333 millivolts. So about a third of a volt. As predicted, it's not a very strong voltage, but it's certainly measurable voltage. It's certainly something to consider. Now in this case, notice that the total magnetic flux has decreased. So it is weaker pointing upward than it was. So if it is weaker pointing upward, then that means that the change is pointing downward. And if the change is pointing downward, then we want to oppose that change, and that means that the magnetic field that is induced, so B induced, needs to be pointing upward. So it was 0.75 Webers pointing upward. Now it's 0.65 Webers pointing upward. So the change, the delta psi, is pointing downward. And therefore, we're going to see that the induced magnetic flux density would need to point upward. So in order to get that, then what I'm going to see here is I'm going to put my thumb in the direction here. So I'm putting my thumb, and I'm going to wrap my fingers around this direction. And you kind of have to imagine putting your right thumb in that direction. And then inside of the coil, then B is going to be pointing upward. So once again, B is pointing upward there. Well, not once again. This is the opposite of the previous example. But now it's pointing upward inside of the loop. So therefore, we can see that the current has to be pointing counterclockwise when viewed from above. Oh, I got that one backwards. And that means that this will be plus on the bottom and minus on the top. And so the current induced is counterclockwise, CCW, when viewed from above. Okay. So again, because it was the positive upward vector decreased, then we had to the induced magnetic flux would have to oppose that change. Okay, here we have a picture that once you understand it, it will be pretty easy to see. We have the three sides, so the top, the left, and the bottom are fixed. Think of that as like a metal frame, and then think of this fourth wall here as being like a rod that can roll, or a rod that can slide, and it's resting directly on top of these top and bottom sort of limits here, so that a circuit is being formed, and that circuit looks like this. But as that rod is sliding or rolling toward the right, then the size of that circuit is going to increase. The size of the loop is going to increase. So we know that if we've got a distance d, and let me just go ahead and I'm going to label this as being a distance x. So we have d and an x. So the area is equal to x times d. And psi, in this case, because the magnetic flux density is perpendicular to the loop, and because the direction of the loop and the direction of the magnetic flux density are not increasing, we can just say that this is b times a, and that is b times x times d. We know that voltage is n d psi dt, but n here is just equal to 1. There is no loop. So this becomes d by dt of b times x times d. But b is constant and d is constant, so therefore this is b times d times dx dt. But dx dt is just the velocity, and we were told that the velocity with which this rod is moving is just lowercase v. So then v, the voltage, is equal to b times d times the velocity. And that is the magnitude of the voltage that appears around this loop here. And then the question is, in what direction is this going to be going? So as the loop gets bigger, then more and more upward pointing vectors are going to be included. So that means that it's increasing the upward component, and so therefore we need to have an induced magnetic field that would be pointing downward. It would be opposed to that change. So as the right hand wall is sliding toward the right, we're gathering more and more upward magnetic flux. So that means that the magnetic flux is going to become more and more upward. We need to oppose that by going downward. And in order to do this, I can again think of putting my thumb in this direction and my four fingers in this direction. And that means that inside of the loop, the magnetic flux is going to be going downward. So that means that the current is going to be flowing in this direction. And it looks like the voltage is actually correct as it's labeled on the figure. So it says, please account for the polarity of the voltage shown when indicating the sign of your answer. So the polarity is correct. So V is positive. If the figure had been drawn with the plus and minus of V in the opposite direction, then I would have had to add a negative sign to that answer. But I didn't, so it's just correct the way that it is. Consider this square loop, which has a time-varying magnetic flux density passing through it. So here you can see that the magnetic flux density is varying with time. There are 100 turns on the coil, and the magnetic field is 45 degrees away from perpendicular. What are the magnitude and direction of the induced voltage and current? Okay, so in this case, we're going to see, well, psi is going to be equal to B times A times the cosine of theta. Even that is a simplification from the surface integral, but it's a simplification that relies only on the fact that B have a constant value across the loop. It's not a constant value in time, but at every point in the loop, it's the same at each instant in time. So this is going to be equal to 10 sine of 2 pi times 60t, and that's multiplied by the area, which is 0.2 meters, the quantity squared, and then that's multiplied by the cosine of 45 degrees, which is 0.28 times the sine, and 2 pi times 60, well, that works out to be 377. To within a tenth or so. So anytime that you see 377 T, I want you to think, oh, that's a 60 hertz signal. Because when you have 60 hertz, that's 60 revolutions per second, and you have to multiply that by 2 pi radians per revolution. So sometimes it'll separate out the 2 pi, sometimes it won't. But the 377, you'll know, oh, that's 60 hertz. That's just the same electricity that would come out of the wall. So V is equal to N d psi dt, and that is equal to 100 times, and the 0.28 is a constant, so I can bring that out in front, d by dt of sine 377t. Well, 100 times 0.28 is going to be 28, and the derivative of the sine is the cosine, so cosine of 377t, but then the chain rule says that I then have to differentiate the thing that's inside the cosine, so that gives me an additional 377, and this is going to give me 10,556 cosine of 377t. And we can't really, I can't really specify the direction because the sine wave is reversing direction 60 times a second, 120 times a second. So the direction of the induced current is also going to be changing that rapidly as well. You might say 10,000 volts out of this system. That seems like a lot. Well, I'll make the observation that a magnetic flux density of 10 Tesla is really high. That 20 centimeters is a decent sized loop. There's 100 turns on this coil, and it is changing very rapidly. That is changing at 60 hertz. So 10,000 is not crazy. I forgot to put the units on here. That's units of volts, of course. Okay, now let's do some specific examples. Faraday's law applied to inductors. I promised you this one last time. I promised that we would derive L di dt. V of L equals L di dt. And so it's time to do that derivation now. This is exactly the same figure that we saw in chapter 15. And we knew from chapter 15 two things. We have an equation for psi sub m throughout the core of this inductor, and we have an equation for L. Well, let's take that equation of psi, and we know that the voltage is equal to N d psi dt, which is N times the derivative of that quantity from equation 15.6. So this quantity just substitutes right into there. Mu is a constant, N is a constant, D is a constant, pi and A squared are constants. The only thing that's not a constant there is I. So everything else moves out in front, and don't forget that this N times this N is where the N squared comes from. And so only di dt remains. And then if you compare this quantity right here, you find that it is identical to this quantity right here. And so therefore, we can substitute an L in for everything in the square brackets, and we end up with L di dt. So everything that was in the second half of chapter 15 really hinged on this equation right here. And I made you the promise that I would prove it to you, and now we have. So there's really not a whole lot else to say about inductors. We've already talked quite a lot about induction, but we couldn't prove the time relationship for an inductor until we had seen Faraday's law. Now, last time we also talked about transformers, and we got some useful results from our discussion of transformers. I mentioned to you that we have step-up and step-down transformers, that they really allow us to distribute, transmit and distribute electrical power from the power plants to the end users. But let's talk a little bit more about these transformers, because there's more to be said now that we have more information from Faraday's law. So I have a single magnetic core that has a voltage and a current on the left, which we're going to call this the primary, and really it's only primary because it happens to be on the left. We'll call the one on the right the secondary. And we know that there's going to be, if you put your thumb in the direction of the current, so your thumb is going to go in this direction, so anyway, if you put your thumb in this direction, your fingers are going to curl in such a way that the current, that the flux density is going to be rotating clockwise. And I've indicated that with some arrows here to show that it is flowing clockwise when viewed from the front. And if you look at the way that the coil on the right is also set, you would put your thumb in that direction, and you would also find that your fingers are coiled in such a way that it would go in the same direction. So these two coils are lined up in the same direction. It would be possible for them to be opposite, and if that were the case, then everything else we're going to see would introduce a negative sign as well. So just be aware of that fact, that you have to line the coils up to be contributing to each other or supporting each other, and if they're opposed to each other, then we would add some negative signs. So a derivation of the relationship between V1 and V2 is really very simple. We know that Faraday's law has to be true for the primary coil, and Faraday's law has to be true for the secondary coil. And we know that Faraday's law says that V1 is equal to N1 d psi m dt. But that same psi m is also flowing through the secondary coil. So V2 equals N2 d psi m dt. We can solve each of those equations for d psi m dt. So I'd say d psi m dt is equal to V1 over N1, and d psi m dt is equal to V2 over N2. And if d psi m dt equals each of those quantities, then they must be equal to each other. And if I had V1 over N1 equals V2 over N2, and then I did a little bit of algebra on them, I end up with this expression that shows me the relationship between V2 and V1. So the ratio of V2 to V1 is equal to the ratio of N2 to N1. And this is known as the turns ratio. So N2 over N1 is what we're going to call the turns ratio. So calculating the ratio of those two voltages is as simple as N2 divided by N1. If I scroll back up here to the original picture, notice then that I could just simply say, let's imagine that N1 is equal to 100 and N2 is equal to 1,000. And if that's the case, then V2 is going to end up being 10 times larger than V1. Whichever coil has more turns is going to have more voltage associated with it. So in that case, I would have a step-up transformer. Or if I had made it be the other direction, then I could have a step-down transformer. So that gives the relationship between voltages, but the question is, what is the relationship between the currents? Because I mentioned last time that if you step up the voltage, there's a trade-off, and that is that you have to step down the current. Well, how much do we step down the current? And the answer is, based on the fact that we're going to assume that there is no power being lost inside the transformer. So that means that P1, the power at the input, is equal to the power at the output. Now that's true to within about 3 to 5% for a modern transformer. So I've got to warn you that nothing is free, and we're going to actually lose a little bit of power in the process, so that the transformation of the current is going to be a little bit worse than what I'm showing you here. But remember that P is equal to I times V, so P1 equals I1 times V1, and P2 is equal to I2 times V2. And then if you were to sort of rearrange this equation, you could get I1 over I2 equals V2 over V1. But we know from the previous discussion that V2 over V1 is equal to N2 over N1. So if you kind of just really pay attention to only these portions of this equation, I1 over I2 equals N2 over N1. And that means that as the voltage is being stepped up, the current is being stepped down. Notice that the I1 is on top, whereas the V2 is in the numerator. And so we're going to find that as we step up the voltage, we have to step down the current. As we step down the voltage, we can step up the current. The last thing that I want to mention is that if you have if you think of the resistance at the primary as being however much voltage at the primary divided by the current at the primary, and the same thing at the secondary, V2 over I2 is the resistance at the secondary coil, we can rearrange this, substitute equation 16.12 by 6, we can next divide equation 16.12 by 16.13, simplify the result, and then substitute the results. So I take 16.12, which is this equation right here. I'm going to divide it by 16.13, which is this equation right here. If they're both equal, I can divide them both. I'm going to rearrange the right-hand side so that it becomes V1 over V2 times the quantity I2 over I1. But I know that this V1 over V2 is just N1 over N2. And because the current is inverse, this is also N1 over N2. If I multiply those together, it becomes N1 over N2, the quantity squared. So whereas voltage and current scale as just the turns ratio, the impedance, the apparent impedance, scales as the turns ratio squared. So this means that a transformer will effectively modify the resistance that's seen on the primary coil when a resistor is attached to the secondary coil. The thing that's attached to the secondary coil will look different than it would if the transformer weren't in place. This is known as impedance matching. Well, it's one of the things that's known as impedance matching. And impedance matching transformers are quite frequently used, especially in audio applications. As it turns out, speakers often have a very low resistance or a very low impedance, and that makes them very hard to drive. It makes it hard, if I've got a voltage source, it's hard to drive a very low amount of resistance because it means you're going to get a large amount of current. Let's see that in example 16.5. A speaker has an impedance of 6 ohms. I have a 12-volt AC source that must not deliver more than 100 milliamps of current. If you try to deliver more than 100 milliamps of current, it's going to overheat. Well, if I try to drive 12 volts into 6 ohms, I'm going to get 2 amps of current. That'd be 20 times too much. So the question is, can I use a transformer to make this system work? And the answer is yes, of course. So I have the transformer right here, and there's going to be a turns ratio. I'm going to have an input impedance, and then over here I'm going to have an impedance that is attached to the output. I know that this is 6 ohms, and I know that I have a voltage source over here, and that voltage source attaches to the primary side, and I know that I want this to be 100 milliamps, and this is going to be 12 volts. Well, looking at the primary first, if I know that I have 12 volts and I know that I have 100 milliamps, well, that must mean that this would be a 120 ohm resistor. So R on the primary side is equal to 12 volts divided by 0.1 amps, which gives me 120 ohms. But R on the secondary side is already specified. R on the secondary side is 6 ohms. That's what's attached to the secondary side. So R on the primary R on the primary divided by R on the secondary is equal to N1 over N2, the quantity squared, which is equal to 120 divided by 6, which is equal to 20. And therefore, N1 over N2 is equal to the square root of 20, which is 4.47. And I can choose N1 and N2 pretty much however I want to satisfy that. I'm going to choose N1 equals 447 coils or turns, and N2 is equal to 100 coils or turns. I could have that times 2, I could have that times 10. It seems like that's a reasonable number of coils to use. So you can see that by adding this transformer, I can really make a difference in being able to drive this speaker that otherwise would have been impossible to drive from that given source. Okay, and then the last and most important example is applying Faraday's law to electrical generators, because without this, we wouldn't have electricity. I mean, with the exception of, I guess, solar power, everything that we use is basically spinning a coil of wire in a strong magnetic field. You think about hydroelectric dams. All they're doing is they're using that water, the potential energy in that water, to spin a turbine, and then that turbine is then causing a wire to spin in a strong magnetic field. Think about a wind turbine, and again, you're causing a wire to spin that's attached to the propellers. A coal power plant. All you're doing is burning coal to boil water to create steam, blow the steam across a turbine to spin a wire inside of a strong magnetic field. Gas-powered generators. I mean, you get the idea. Everything pretty much except for photovoltaic solar energy is going to be using gas-powered generator. I'm sorry, it's going to be using a wire spinning in a magnetic field. Now, I'm trying to show you here the cycle, just so you have a picture of what's happening here. I have a loop of wire. The red and the blue side have no physical significance, but I'm just trying to show which direction the loop is rotating. So we start out with it being horizontal, and so here it's horizontal, and then we're going to move over here to the right, and it has spun in this direction. So the blue that used to be to the right is now up, and the red that used to be to the left is now down. We come down to the bottom right, and now the red and blue have reversed directions. So they're once again parallel to the magnetic flux, and so here we basically, there's no flux passing through that loop. And then when we come over here to this last example, now it's again perpendicular to the magnetic flux, and so we have 100% flux flowing again. So one thing that I'm going to observe is that here I know that that the psi is equal to 0, and over here psi is equal to 0, and up here psi is the max in one direction, and over here psi is the max in the opposite direction. And so what I'm seeing here is I'm expecting that there's going to be some sort of a pattern where the voltage is going to be 0, or it could be that the voltage is going to be 0, it's going to reach a max, it's going to go back to 0, it's going to go down to a max in the opposite direction, back to 0. That's making me think that it's either going to be like a triangular wave or a square wave or a sine wave. As it turns out, the dot product between B and A is going to cause this to be a sine wave. So we see here that we have psi sub m is equal to the surface integral of b dot ds. So that's b times a times the cosine of theta. B is totally constant. B is not moving at all. A is going to be a constant quantity that is rotating, and the rotation is represented by that cosine of theta. So now we're going to apply Faraday's law to calculate the voltage across the output terminals of the generator. So Faraday's law says N d psi dt. So it's N times d by dt of b, a, cosine theta. But b and a are constants. So we pull those out in front, and we end up with N b a times d cosine theta dt. And the derivative of the cosine of theta is the negative sine of theta, and then the chain rule adds a d theta dt onto the end. And that d theta dt, we represent that as omega. That's the angular velocity. So we end up with negative NBA omega sine of theta. So this negative sign, honestly, you can pretty much ignore the negative sign because it's obviously a sinusoid, and so it's going up and down and up and down. That's just introducing a phase difference. So we see that the strength of the voltage is going to increase as the number of turns increases. I would totally expect that. Strength of the voltage will increase as the strength of the magnetic flux increases. I would expect that. It'll increase as the surface area increases. I would expect that. Interestingly, it also increases as the rotational angular velocity increases. I guess that seems reasonable. I might not have guessed it, but the faster that things are changing, then the higher the derivative is going to be. So that seems reasonable as well. And then we also have a sine of theta, and that shows that the voltage is in fact going to be going up and down as a sinusoid. So what we find then, very importantly, is that we can have a voltage generated by a simple system, a constant magnetic field with a loop rotating in it, and it will generate a sinusoidal or AC voltage. So this is one of several reasons why AC power is used so frequently. It's really easy to generate. As a matter of fact, all you have to do is just spin a coil of wire in a magnetic field and you get AC voltage all day long. Now you have to have a way of spinning the coil of wire. If we were working in the lab, you might use your hand to spin it, but you can't use your hand to spin it fast enough and with enough torque to be able to generate electricity on any sort of a significant basis. So we're going to need to have some sort of an energy source to create that rotation. As a matter of fact, AC power is so easy to generate that if you wanted to generate DC power, you would probably generate AC first and then rectify it, convert it into DC in order to get the DC voltage. So even if that converter costs us a few percentage points of inefficiency, that's probably the way that we would generate DC voltage. So what is the magnitude of the voltage output by a generator with a cross-sectional loop area of 2 square meters, 1,000 turns, B is 10 Tesla, and the rotator is rotating at 3,600 RPM? Well, the first thing I'm going to do is I'm going to fix this 3,600 RPM. I need to know omega. Omega has to be in radians per second. And so omega is equal to 2 pi times F, because F is revolutions per second, and the 2 pi is radians per revolution. So this is equal to 2 pi radians per revolution multiplied by 3,600 revolutions per minute. That's what RPM stands for, revolutions per minute. And then that's multiplied by, I've gotten rid of the revolutions, but I need to convert minutes into seconds. So I need this one to say minutes on the top and seconds on the bottom. And if I do that, then the minutes will cancel, and then I'm left with radians per second, which is exactly what I need. So if I need minutes per second, well, there's 1 minute, and there'd be 60 seconds. So then I can do this calculation, and I end up with our old friend 377 radians per second. Because 3,600 revolutions per minute is 60 revolutions per second, or 60 hertz. So I'll say the magnitude of, and I never know whether to make the V capital or lowercase, but because there's also sometimes velocities associated with these problems, I'll leave the voltages as being capital. This is equal to NBA times omega. If I scroll back up here, remember that NBA omega is the magnitude of this expression, and the sine of theta just has the magnitude of 1, and I'll omit the negative sign. So NBA times omega is going to be equal to 1,000 times 10 Tesla times 2 square meters times 377 radians per second, and that gives me 7.54 megavolts. A very large amount of voltage. But this is a big coil rotating very fast with a very strong magnetic field. This would be like at the very heart of a power plant. This is the sort of generator that you might find in a circumstance like that. Okay, so those are our examples. We've seen pretty much every example of what Faraday's law can do. Let's look at the final form of Faraday's law. We're not going to add anything. We're not going to change anything. We're just going to represent it in a different way. So we're going to make it a bit more mathematically complex, which I guess to me kind of seems to hide the significance. Remember, it's not hard. V equals N d psi dt. I wish somebody would have taken me aside when I was 20 years old and said V equals N d psi dt, because what I got was this big formal official version of it. Let's just remember that we know that the voltage is equal to the line integral of E dot dl, and we can substitute that into the left-hand side of our first representation of Faraday's law. Notice that the negative sign has come back. I'll leave it in because it's the official version, and the negative sign there does represent Lenz's law. So it used to be V of t equals negative d psi dt, but now it's the line integral of E dot dl equals negative d psi dt. But we also know that we have an expression for psi, and so we can represent this quantity right here represents psi. And so it's the surface integral of B dot ds. That came from equation 16.2, but I'm going to erase that because I don't want to sort of draw away from the splendor of Faraday's law in its final and official form. Sometimes it's referred to as Faraday's law, sometimes it's called Faraday's law of induction. Those are the same thing from everything that I can tell. So, because this is the big formal version of the equation, I wanted to have the big formal version of the name. And this now is one of Maxwell's equations. It is the third that we've officially added. Remember that we basically had Gauss's law, and then we had, you could think of it as Gauss's law for magnetic fields, that there is no divergence of a magnetic field, it's equal to zero. This is now Faraday's law, which relates electric fields to magnetic fields and with a derivative in there. We have one more equation to be added, and that'll happen next time in chapter 17. So, Stokes Theorem, which I'm not going to take a lot of time here to talk to you about Stokes Theorem. I'll just mention that Stokes Theorem basically says if you have a region, and within that region, there's a lot of little rotations happening. So, imagine that it's kind of a complicated circumstance where there's lots of things that are rotating, and as they're rotating, they're all adding together to create a circulation around the perimeter. Right? You can imagine if there are all these little local rotations, then there would be these big circulations around the perimeter as well. What we find then is that this circulation around the perimeter of that loop is equal to the surface integral of the curl. So if you add up all the little loops inside, they add up to the one big loop on the outside. And so this is the curl, and this is the surface integral. Now, we could, if I can just kind of wave my hands at that, and you might go, okay, I accept that. Or, if you'd rather, you can say, prove Stokes' theorem to me, and, come by my office. I'll find a proof and show it to you, but just trust me when I say that it's a happy world in which you're an engineer, because you don't have to worry about these proofs. You can accept them and know that mathematicians have done the proof for us, and then we can apply that proof. So what I'm going to do is I'm going to take our previous version, 16.21 at the top of the page. I'm going to, instead of the left-hand side used to be the line integral of E dot dl, but this says the line integral of E dot dl is equal to the surface integral of the curl. So now that surface integral of the curl it has gone in its place. So the surface integral of the curl becomes the left-hand side, and we're going to move the derivative inside the surface integral. So this derivative right here is moving inside the surface integral. Again, there are some requirements, some mathematical requirements that would say, it has to be a continuous function. It can't have impulse functions right at the surface, and I will assure you that those requirements are being met. So we can, in fact, move the derivative inside the surface integral. And what we find then is that we have two surface integrals of two quantities over exactly the same surfaces. So notice that that's over delta S, that's over delta S. There's a negative sign here, don't forget the negative sign. If two surface integrals of two different quantities over the same surface are equal, then the quantities must be equal. And so we find that the curl of E is equal to negative dB dt, and that means that is the point form of Faraday's law. So this is the point form of Faraday's law of induction. So we have both the integral form and we have the point form, and we can work with both of those equations. So today we've seen some important results. Maybe the most important results we're going to see the entire semester. Well, there's one coming up in a couple of chapters that's at least this important. So I don't want to oversell this, but Faraday's law is extremely important. V of t is equal to n d psi dt. That is Faraday's law. And Lenz's law, which sometimes is represented with a negative sign in Faraday's law, says the induced voltage and the induced current that corresponds to that voltage will be in a direction that opposes the changing magnetic flux. So that whatever the change is, we're going to oppose that change. If it's becoming more positive upward, then our induced current is going to be pointing downward. If it's becoming less positive upward, then the change is actually negative, and then our induced current would be pointing upward to counterbalance that change. We have a more formal version here for the calculation of the magnetic flux, and then we have proven that V of t is equal to L di dt. We studied transformers, and we found three equations that relate the voltage, the current, and the resistance at the two sides. For generators, we found a relationship between the number of turns, the magnetic flux, the surface area, the speed of rotation. We can use that all to calculate V of t. And then the formal official version of Faraday's law can be written in integral form and in point form.